In this video, we will try to solve some numericals related to the first law of thermodynamics. So this is the first question. A stationary mass of gas is compressed without friction from initial state of 0.3 meter cube and 0.105 megapascal. So let us try to understand this question with a diagram. So this is the initial state of the system, and then it has been compressed to a final state of 0.15 meter cube and 0.105 megapascal pressure. So if you notice here, the pressure is constant, the pressure remaining same during the process. There is a transfer of 37.6 kilojoule of heat from the gas during the process. So they are asking now to find out how does the internal energy of the gas change. Okay, so let us start the problem. Given data P1, V1, P2, V2, Q, all these things I have written. P1 is equal to P2 can be written as equal to P, that is the pressure is constant here. Okay, so by applying the first law of thermodynamics, we know that Q can be written as the summation of del U plus W. We have already seen this in the previous lectures. So since this process is a constant pressure process, so work done during the constant pressure process can be written as the integration of P into dV, whereas the P is constant and the volume varies from V1 to V2. Okay, so if I break this, then I can write it as P into V2 minus V1, whereas V2 is the final volume and V1 is the initial volume. So directly I can put the values since these are given in the question. So finally I can find out the answer is minus work done is minus 0.0157 megajoule. Okay, so if I write it in terms of kilojoule, because in the question everything is given in terms of kilojoule, it will be minus 15.57 kilojoule. So minus means work has been done on the system. That this is why they have it has come as minus. Since we are compressing the system, so we have done work on the system. Okay, now putting the value of work done in equation 1, in this equation we will get that Q is equal to minus 37.6, and already we have got the value of work done as minus 15.75. So finally the change in internal value internal energy has been obtained, which is nothing but minus 21.85 kilojoule. Okay, so this was a very simple problem. Let us try to solve the next problem. In the next problem, it says that when a system is taken from state A to state B along the path ACB. So let us try to first identify these two states, state A to B. These are the two states A and B, see in the graph. So if a system is taken from A to B along the path ACB, 84 kilojoule of heat flows into the system and the system does 32 kilojoule of work. So now they are asking, number one, how much heat will flow into the system along the path ADB. If the system moves along the path ADB, how much heat will flow into the system if the work done is 10.5 kilojoule. Okay, next, if the system returns from B to A, suppose it is returning from B to A through this path, curved path, the work done on the system is 21 kilojoule. Now they are asking, does the system absorb or liberate this heat? And finally in this third part, if the internal energy value at state A is 0 and at state D is 42 kilojoule, what will be the heat absorbed in the process AD and dB? Okay, so let us start the problem. First, along the path ACB, we have Q is equal to 84 kilojoule and W is equal to 32 kilojoule. Now we have to find out what is the heat transferred in the process in the path along the path ADB. So again, by applying the first law of thermodynamics, I can write it write the law as Q ADB is equal to del U plus W ADB. Now WADB is already given in the question. It is 10.5 kilojoule. but we do not know the value of del U. Okay, so del U can be easily found out from the other path. Since del U is a internal energy is a point function, so del U will be change in internal energy will be same along different paths ACB, AB or ADB. So from if I take help from the path ACB, I can write it as along the path ACB Q and W values are given. Already these are given in the question. So directly if I apply the first law here, del U value can be found out, and it has come around 52 kilojoule. Okay. Now if I plug it, if I put this value back in the equation 1, I can get the heat transferred in the process QADB. Okay. So the first part of the problem is solved. Now in the second part, they are asking to find out Q B to A. When the system returns from B to A, what is the amount of heat transferred? So it is given in the question that minus 21 kilojoule of work has been done on the system, and del U AB is 52. Okay. Now if del U AB is equal to 52, so del U B to A will be minus 52 because the system is coming in the opposite direction. Okay. Just for the sake of understanding, I am sharing one thing. The change in internal energy is the difference between the internal energy at the final state minus initial state. So del U AB can be written as UB minus UA. So consequently, del U B to A can be written as UA minus UB. So the magnitude will be always same, but the minus sign will be different. Fine. So now if I apply the first law of thermodynamics along the path QBA, it can be written as the summation of change in internal energy del U and work done. So both these values we already have with us. So if I put it, I'll get the QBA can be written as minus 52 minus 21, which will be coming around minus 73 kilojoule. Okay. Now again, if I go back to this question, the last part is left. If UA is 0 and UD is 0, what will be the heat absorbed in the process AD and DV? So let me refer to this diagram. They are asking to find out AD and DV. So QADB can be written as QAD plus DB. I have simply broken the path QADB into the two process. Okay, from this graph I can write this. So QDB can be written as QADB minus QAD by rearranging. QADB is 62.5 kilojoule. Already we have this in the question, but we do not know the value of QAD. So QAD, let me give this equation a name. Let it be equation number 2. Now to find out QAD, let me apply the first law of thermodynamics in the process AD. So QAD can be written as del UAD plus WAD. So let it be equation number 3. Now to find out WAD. So W again the WADB, this entire path can be written as W work done during the process AD plus work done during the process DB. Okay. Now since just look at the diagram graph in the right hand side, since DB is a constant volume process, so we know that during constant volume process the work done is 0. So WDB will be 0. So if I put it in the equation, WADB will come as 10.5 kilojoule. Okay. Sorry, WADB is given as 10.5 kilojoule. So WAD will also be 10.5 kilojoule since WDB is 0. Now putting these values in equation 3, I get equation 3 was QAD is equal to del UAD plus WAD. So if I put it in the equation 3, what I get is del UAD is already given as 42 kilojoule and WAD is 10.5 kilojoule I have got, So QAD will be 42 plus 10.5 kilojoule, which is nothing but 52.5 kilojoule. Okay. Now finally, if you refer to this graph, QADB can be written as QAD plus QDB. Already we have discussed this. So if I put the value of QADB, since it is given in the question, and QAD I have already got now 52.5. So finally I will get QDB. So QDB is 10 kilojoule. So final result is QAD is equal to 52.5 kilojoule and QDB is equal to 10 kilojoule. These two things we had to find it out. So this was all for today. We will solve some more numericals in the next video. Please keep supporting Meg Vidya. Thank you.